Hello and welcome everyone for the first day of our Wiley Analytical Science virtual conference. For the third time, we have put together an exciting program for you with 15 insightful and interactive sessions with key experts in various different application areas. My name is Christina Pogel. I'm the product manager of Wiley Analytical Science, and it's a great pleasure for me to open the virtual doors to our conference for the third time. And here with me for the first presentation of this conference are Dr. Viola Schäfer, Market Manager R&D, and Pascal Wielsch, Development Engineer, both from Pfeiffer Vacuum. In their presentation, Viola and Pascal will describe how you can reduce vibroacoustic emissions of your turbopumps. So you will get many useful tips and tricks, and you will also have the chance to ask all your questions to our two experts by submitting them into the questions box. They will be answered during our Q&A round right after the presentation. So now I will hand over to Viola, who will begin with the presentation.
Thank you, Christina, for your kind introduction, and welcome to our webinar. In today's presentation, you will learn how secondary pump characteristics like vibroacoustic emissions can influence your application, your experimental result. For example, if you're running an electron microscope. We will discuss how the laser balancing technology improves secondary pump characteristics of turbopumps, and therefore how this new technology leads to advantages for your application like microscopy and mass spectrometry. My name is Viola Schäfer, and together with Pascal Wielsch, I will be the speaker of today's webinar. I will begin with a short overview of vacuum. Why do we actually need vacuum to run applications like mass spectrometry or electron microscopy? So therefore, I will give you a short overview of vacuum and the basics of vacuum technologies before I will go on with the generation of vacuum. Here, I will mainly focus on turbopumps and the different pump characteristics, the already mentioned primary and secondary pump characteristics. Then I will hand over to Pascal. He will short introduce the unbalance topic. So he will give an overview what an unbalance is in general and why do we actually need to balance a turbopump rotor. Before he then will explain in a bit more detail different balancing methods and the advantages of the new developed laser balancing technology. So let us start with a short overview of vacuum and the question, why do we actually need vacuum? Therefore, I would like to start with an overview of vacuum by Paul Scherrer Institute. And as you can see here, the technical definition of vacuum is shown in this column. So vacuum is, technically speaking, defined as a pressure below atmospheric pressure. So all pressure ranges below 1000 hectopascal are called vacuum. Pascal is the SI unit of the pressure, so that's why I will always use Pascal. In Europe as well as in Germany, it's more common to use bar, but it's quite easy. So 1 hectopascal is the same as 1 millibar. So from 1000 to 10 to the power of -3 hectopascal, we are talking about backing pressure. In pressure ranges between 10 to the power of -3 down to 10 to the power of -7 hectopascal, we are talking about high vacuum, and all pressure ranges below 10 to the power of -7 hectopascal are called ultra high vacuum. So as you can see in the next column, if you are decreasing the pressure, you're also decreasing the number of molecules in a given volume. But as you can see here, about 10 to the power of -7 hectopascal, we have still 10 to the power of 9 molecules left in 1 cubic centimeter. So you have less molecules, but it's not empty, because by the Latin word vacuus, that would mean empty. So by the word, the meaning of vacuum would be empty space. But it's not true. So you have still many molecules left in 1 cubic centimeter. But if you decrease the number of molecules in a given volume, you increase the mean free path, as you can see here in the next column. So if you are decreasing the number of molecules, you will increase the mean free path. That's a very important point for vacuum technology, and I will give a bit more details on the next slide. If you decrease the number of molecules, this will also influence the surface. So if you want to analyze the surface of a substrate, then it's also important that you have less molecules, an increasing mean free path, because it will lead to a clean surface. You can also see different vacuum pumps and their operating ranges here. So we will talk about turbopumps later. And as you can see here, turbopumps are working in the backing vacuum range down to the ultra-high vacuum range. You will also already see some typical vacuum applications. For sure, there are many more, but here you can already see the electron microscopy. And as you can see, you need backing vacuum down to ultra-high vacuum to run an electron microscope. As I already mentioned, I will define the mean free path now. So the mean free path is defined as the distance a molecule can travel in a vacuum chamber before it collides with another molecule. So this mean distance is called the mean free path, and it's quite important for many applications. And as you can see here in this diagram, you can see here down the pressure. And if the pressure is decreased, the number of molecules in a given volume is also decreasing, and therefore the mean free path is increasing. And this is very important, for example, for mass spectrometry. So if you are thinking of a time of flight mass spectrometer, for example, here you can see a mass spectrometer from waters. And here we have a so-called flight tube. Mass spectrometers also always consist of three parts. So you have an ion source, you have an analyzer, and you have a detector. So at the beginning, we have molecules, and then after ionization, we have ions, and these ions will enter the flight tube here, and then they need to travel the whole distance without colliding with other molecules before they reach the detector. And therefore, you need a mean free path which is high enough so that the molecules can travel the whole distance without colliding with other molecules or with other ions in this case. As you can see here again, in the pressure range of 10 to the power of minus 6 hectopascal, we have a mean free path of about 100 meters. So without vacuum, it would not be possible to analyze molecules in a mass spectrometer. Now I would like to talk about different reactions of gas molecules or gas atoms in vacuum. So please consider you have a vacuum chamber. This is the wall. So on one side we have atmospheric pressure. That means we have many, many molecules. And on the other side of the wall, we have vacuum conditions. So we have less molecules in the space. And one reaction we can observe is the adsorption. So gas hits the surface and sticks to it. So this is the so-called adsorption. A reaction which can follow to adsorption is absorption. So a gas incorporation into the chamber wall, for example. This reaction is reversal. So after absorption, it's also possible that the gas will desorb again. So it's released again into the environment. We can also observe diffusion. Diffusion is a transport of one medium into another medium. And this medium can be solid, liquid, or gaseous. It's shown here. So the gas molecules are moving in the chamber walls. Very interesting reaction is the so-called permeation. Permeation is the sum of different reactions. So the first step, we have adsorption, for example, here at the atmospheric side, then a diffusion process through the material. And then on the other side, the molecules or the gases, they can desorb again so that the gas travels from one side of the chamber into to the other side, so into the chamber. And the last reaction I would like to mention is the leakage. So if you have a leakage, leakage is defined as a hole or a porous area in a wall, so that the gases can travel from the higher concentration side towards the lower concentration side. So these are different reactions we can observe in a vacuum chamber. So gases can react in these ways. And now I would like to talk about absorption. Because if you consider you want to do a surface analysis, then you want to have clean surfaces. And absorption, this can influence your experiment. So for surface analysis, like electron microscopy, or if you're thinking of scanning, tunneling microscopy, you want to have a clean surface. And for sure, again, we need vacuum to run the application. So the column needs at least high vacuum conditions, while the filament is already needs ultra high vacuum conditions. And now if you want to analyze the surface, you want the surface to be clean. And a question you can ask yourself is, how long is the surface of my substrate uncovered? So how much time do I have to analyze the clean surface? And one number which gives you an indication is the so-called area impact number. You can see it here. So the area impact number indicates how many particles per area and per time hit the surface. And this area impact number, for sure, it's depends on the pressure in the chamber, on the Boltzmann constant, the mass of the gases, as well as on the temperature. And this will give you a clue how long the surface is uncovered if you assume that every molecule which hits the surface will adsorb to it. For sure, in real life, not every molecule which hits the surface will stick to it, but it's a kind of rule of thumb. So if we consider high vacuum conditions, 10 to the power of minus 6 hectopascal, we have 10 to the power of 15 particles per second and per square centimeter, which adsorb on the surface, because so many particles will hit the surface. Then we have one layer, so we have a monolayer within 1 second. So you will not be able to analyze the surface, the clean surface, because it will be covered within a second. But if you have ultra high vacuum conditions, so 10 to the power of minus 10 hectopascal, you will have at least 2 hours time to analyze your clean surface. As I already mentioned, we assume that every molecule which hits the surface will adsorb to it. In reality, it's a bit different, but it will just give you an idea. It's a rule of thumb, so just to give you an idea why vacuum is needed. So we need vacuum to have a clean surface and to have a mean free path which is high enough so that the molecules can travel a long distance without colliding with each other, so that they can, for example, reach a detector of a mass spectrometer. Now I talked a long time about vacuum. Why do we need vacuum? But how can we generate vacuum? And therefore, we will focus on turbopumps and on the primary and secondary pump characteristics and the influence of these characteristics for your applications. If you want to pump down an experimental chamber, for example, a mass spectrometer, you will need different pumps because you have to achieve different pressure ranges. So with a turbopump, as I already mentioned, you can not work at atmospheric pressure. So you need a second pump, a so-called baking pump, to bake the turbopump. So this means pumping is teamwork. If you want to achieve ultra-high vacuum, as you can see here, we have, for example, a chamber. Then the main pump, the turbopump, is connected to the chamber. The turbopump transports the gases away from the chamber towards the backing pump, for example, a scroll pump or a rotary vane pump. And then the backing pump is compressing the gases towards atmosphere. And then you can achieve ultra-high vacuum. Now I will only focus on turbopumps. And therefore, it is important to now know how a modern turbopump is designed. And here you can see a picture of a hybrid levitated turbopump. If you have a hybrid bearing, you have a combination of a permanent magnetic bearing here at the top of the pump near the high vacuum flange. And down here, we have a ceramic ball bearing near the fore vacuum flange. Besides, for sure, we need a motor and a rotor shaft where the rotor plates are connected. And we have also stator plates. Okay, the gas atoms or molecules, they will enter the turbopump here at the high vacuum flange. They are then accelerated towards the fore vacuum flange, and they will leave the pump here at the fore vacuum flange. For the pumping speed, or to have the turbopump running, to have a certain pumping speed, it is very important that the rotor is rotating very fast. And we are talking about a rotor speed of up to 90,000 rounds per minute. So it's rotating very, very fast. And you will understand that it's crucial for the pump performance that the rotor is balanced very well. And the bearing down here, this is always a source of vibration as well as of noise. But if you improve the balancing of the rotor, you can also improve the vibrations. So that means you can reduce the vibrations as well as the noise. Now, I would like to give you a bit more details on the different pump characteristics. I already mentioned that we will talk about how to reduce secondary pump characteristics like vibroacoustic emissions. But let us start with the primary pump characteristics, which are pump performance concerning characteristics. And I think you will all know different pump characteristics like the ultimate pressure or the pumping speed, the gas throughput or the compression ratio, which are all characteristics which you can find in a technical data sheet. Besides the so-called primary pump characteristics, there are also some secondary pump characteristics. For example, the size or the compactness. As you can see here, the Hi-Pace A2 Neo, which is the most compact turbopump in its pumping speed class. So the pumping speed as a pump performance concerning characteristic is used to classify the pump. And the size compactness, it's a secondary pump characteristic, but it's also very important because if you have a plant, if you have an experimental chamber, maybe you do not have that much space, you want to have a compact design, it's very important to have a small and reliable pump. Another secondary pump characteristic is the resistance against radiation. This is, for example, important if you're thinking of accelerators where we have high radiation, and this radiation can harm the electronics of a turbopump. So if you want to run an accelerator, it's important so that the electronics are not damaged by the radiation. And last but not least, secondary pump characteristic, which I want to mention, is the noise vibration harshness. And especially in this field of secondary properties, the requirements for turbopumps have increased over the last decades. And this is why 5 Vacuum developed a new laser balancing technology to reduce the vibroacoustic emissions. But now I would like first to explain a bit more about the pump performance concerning characteristics, the so-called primary characteristics. Here you can see as an example the ultimate pressure of a turbopump, which is defined as the lowest achievable pressure. And that means that we have the gas which is transported away due to the turbopump. But we have also not only the gas which is transported away, we have also backflowing gas through the turbopump. And in some point, you will reach an equilibrium between the gas which is pumped away and the gas which is flowing back. And this is the so-called ultimate pressure. Another important primary pump characteristic is the pumping speed. The pumping speed is a movement of a volume per unit time. For example, this pump here is able to transport 21 cubic meter within 1 hour. For turbopumps, another unit is more common. So, for example, the Hypace 80 Neo can transport 67 liter within 1 second. So it's an important characteristic to classify turbopumps. But as I mentioned, the secondary characteristics are getting more and more important due to an increasing application requirement. For example, in the field of microscopy or mass spectrometry. And for this applications, there is a need to reduce the so-called noise vibration harshness. As I already mentioned, the bearing, you can see it here again, the ball bearing down here is a source of vibration. Here at the top, we have the permanent magnetic bearing. And in case of ball bearing, due to the limited number of balls, there are also generation of mechanical noise. And the task is to reduce the noise vibration harshness to improve the secondary pump requirements. And I will show you why this is important. So if you think of a laboratory workspace, as you can see it here, for example, here with a benchtop mass spectrometer device like the GSD350, which you can connect to a thermobalance. Here in front, maybe the worker is sitting, and you do not want to have much noise. And you do not have only the turbopump. For sure, you have different accessories in your workplace. So you do not only have the turbopump. There are other sources of noise. So you want to reduce the noise of every single source. So therefore, it's important to reduce the noise vibration harshness. Another example is the influence of the vibration of a turbopump. And as you can see here on the image on the left side, here, this is an image by an electron microscopy where a vibration amplitude of 20 nanometer was measured at the high vacuum flange. And if you compare this picture with the picture here on the right side, where a vibration amplitude of 5 nanometer was measured at the high vacuum flange, you can see that here on the right side, this picture has a higher resolution than the one on the left side, only due to the fact that the vibration amplitude was at the high vacuum flange was lower. So this means you can see here how the vibration of a turbopump can influence the experimental result of an electron microscope. Please keep in mind, the vibration depends not only on your turbopump, it's just an example. So the turbopump for sure influences your application due to the fact that it vibrates, that it has some vibrations, but for sure there are also other parts of your experiment which are also a source of vibration. Also the chamber does influence your experiment. And for many applications, it's more important to have lower amplitudes of vibration in other frequency ranges. So just keep that in mind. Yes, the turbopump is a source of vibration, but there are for sure some more. So here you could see on the last two slides how the secondary pump requirements can influence your experiment. But Pfeiffer Vacuum was able to reduce the vibroacoustic emissions by inventing a new technology to balance a turbopump rotor. It's not that easy because balancing of a turbopump rotor is a challenging task due to the very high rotational speed. Pascal will give more details on this, but as the balancing influences the secondary pump characteristic, it's a very important topic. The balancing is a core competence of Pfeiffer Vacuum, and therefore it's constantly being improved. And in the next slides, you will see how the balancing was done in the past and how we will in future balance the turbopump rotors, which is very important for low vibroacoustic emissions for different applications. So on the next slides, Pascal will focus on the balancing technology. He will mention what an unbalance is in general, and then he will explain different balancing methods and the advantages of the new laser balancing technologies. And with this, I will hand over to Pascal.
Yes, thank you, Viola, for this first part of this presentation. First of all, hello everyone, my name is Pascal Wielsch, and in the following 2 chapters I will focus on unbalance and balancing methods. So yeah, let's start off with the first slide, so the topic unbalance. So the first question we have to answer is, what is an unbalance? And on this slide I will explain this phenomenon on an everyday life example, a simple car tire. So we all probably do have points of contact with the subject of balancing in our daily lives in the automotive sector. So every new car tire needs to be balanced first before it's mounted at the car. So unbalance as a physical phenomenon is commonly known as centrifugal force. And the definition says that a rotor unbalance is a condition in which vibratory forces and movements are transmitted to the bearing because of unbalanced centrifugal forces. And now there are several negative effects. So unbalances generate centrifugal or radial forces that are transmitted via the wheel suspension to the whole car. So an excessive unbalance in a car tire can then generate high radial forces, and they lead to vibrations in the steering wheel. And in the best case, that's only annoying for the driver, but in the worst case, that can cause damage of different components. So now it's a fact that even bodies that appear symmetrical from the outside, they have in reality small inequalities in their mass distribution. And such an unequal mass distribution leads to an unbalance. And on this slide, I want to point out the relevant main causes for unbalance. So I already mentioned the first cause, the inhomogeneity of the raw material. But also the manufacturing process of a component. So for example, when we imagine we have inaccuracies or errors during the machining processes, that could be another cause. Or furthermore, the construction as well as the assembly of a rotor can influence the unbalance of a rotating system. But unbalance can also occur and increase during the operation of a pump or of a rotor because of wear and deposition due to harsh processes, for example. So in order to understand the phenomenon of an unbalance, I will use a simpler example of a disc-shaped rotor with minimum axial extension. So let's think of a tiny mass particle on this disc-shaped rotor with a mass m at a given radius r, so the distance to the bearing of this rotor. And when this rotor now is spinning, spinning with the rotor speed omega, we can calculate a radial force with this equation here. And so now we have on this disc-shaped rotor, we have many single mass particles that you can see here for an example. And each of these mass particles generates a single individual radial force. And what we now can do is that we can use the vector sum of all these individual unbalance vectors. So we can use this equation to calculate the resulting radial force that acts on the bearing of a rotor. And now when this resulting radial force is 0, then this rotor doesn't have an unbalance. But in most cases, the force is not equal to 0. So we can see that a rotor has an unbalance that generates a radial force. And now we can describe the unbalance condition a little bit different by using a single unbalance like this. So this single unbalance now again has an unbalanced mass U at a given radius r, and we can calculate the radial force, the resulting radial force using this part of this equation here. And to determine the unbalance, we can also use another equation. So I show you a lot of equations. The last one here, and the typical unit of an unbalance is gram times millimeter. And now I want to continue. And now I think that we understand basically what an unbalance is. I would like to focus on the question, why do rotors need to be balanced? So as we can see in this animation here, again, we have the same disc-shaped rotor with an unbalance. And when we have a look at the animation, we can see that an unbalanced rotating disc generates rotational forces. And these forces depend, as I said, on the level of unbalance, but also on the rotor speed. And This does have a large impact on turbopump rotors because we have, as Viola already mentioned, we have very high speeds of up to 90,000 RPM or 1500 Hertz. So the slightest unbalance of a few milligram can have a very strong influence, and that's because of the quadratic behavior of the rotor speed. So unbalanced turbopump rotors are not operable with higher speed, or they can experience damage of rotor or other components of the pump, and therefore the requirements for the minimization of unbalance are extremely high, but they lead to a smooth and damage-free operation for many years. They help to minimize vibrations, and that also guarantees that we have lower vibration that are transmitted to the vacuum chamber and the customer application. To sum this all up, so to answer the question, why do turbopump rotors need to be balanced? As I said, the general effects are that we have higher rotational forces, higher rotational radial forces, and that results in an additional load on the bearing arrangement. So we can have an increased wear and possible damage of components, as well as increased vibration. And as I said before, these vibrations are transmitted via the bearing to the pump housing and other mechanically coupled components of the customer application, for example. So the process of balancing now is the compensation of an uneven mass distribution. So from the unbalanced causes that I have shown some slides before, we can see that each rotor, so even in a series production, has its own unbalanced distribution. So therefore, a balancing process is necessary in the production step of a turbopump rotor. The target now is to check and correct the mass distribution of each single rotor. And we have defined tolerances that determine whether the mass distribution is okay or if it needs to be corrected. And this mass compensation is based on another equation that you can see here. And so now, again, let's think of this disc-shaped rotor with an unbalance. And now we have to be sure that we apply a correction mass UA at the right correction radius in contribution to this equation. And this mass compensation takes place in a correction plane that is perpendicular to the rotor axis. And now we have, or basically we use two different methods. So on the one hand, we can do a positive mass compensation. And in this case, we apply a mass on the opposite side of the unbalance vector. And that's the example of our car tire that is balanced with balancing weights. And on the other hand, we also can do a negative mass compensation. And in this case, we need to remove mass. So we have a negative correction mass in the same angular position like the unbalanced vector. And machining processes like drilling, milling, or grinding are widely used in engineering. So on this last slide to that main theoretical topic of unbalances, I want to explain the unbalance condition using the example of a general rotor. So in reality, a rotor has a certain actual length and needs to be considered as a three-dimensional object. And because of this fact, an infinite number of unbalances can occur, and we cannot measure we cannot measure this. So we have to find a solution. And now the assumption is that we divide our general rotor into several rotor elements that are, again, disc-shaped rotors with little actual extension. And here in this figure, you can see now we divided the rotor, for example, in 8 disc-shaped rotor elements. And now each single rotor element has its own unbalance vector. So we have an unbalanced distribution. We have a finite number of vectors, and the unbalanced state is sufficiently described. What we now can do is, for a simplification, it is possible that we merge several unbalanced vectors into the desired balancing planes for our next step, the correction. So this method depends on the occurring unbalance type. And in this example, for example, we can build the vector sum of all these individual unbalances to get the resulting unbalance UR in that plane here. And that plane, we also call them balancing planes. As I already mentioned, they are perpendicular to the rotor axis. So let's jump into the next topic, topic number 4. So I want to focus on the balancing methods, and I want to explain especially the advantages of our developed laser balancing technology. Okay, so for a long time, Fiverr Vacuum has been using the conventional balancing technology to perform the mass compensation of the turbopump rotors. And on this slide, I want to show you the general procedure. So first of all, the to-be balanced rotor is assembled in a special balancing machine. And I displayed an example rotor at the top of the slide here. In the next step, we accelerate the rotor to a fixed balancing speed, and because of the unbalance, we have vibration, but we also have a radial displacement of the rotor, and this radial displacement is measured in 2 measuring planes that are close to the bearing with distance sensors. And the next step, step number 3, is the unbalance calculation, and here we use a special calculation algorithm that solves this equation here. So the radial displacement was already measured in the previous step, and now we use the influence coefficient matrix A to calculate the unbalance of each single rotor. And when we want to balance a new rotor for the first time, we have to determine this coefficient matrix A by screwing in several test weights. So with these test weights, we have a specific mass, and we mount that in a fixed balancing hole in a specific balancing plane. And so we change this equation. We know our test unbalance. We measure again the radial displacement, and so we can calculate the coefficient matrix A. And this coefficient matrix now describes the system of a rotor in our balancing machine, and we can use this coefficients for every series rotor with the same geometry. So as I said, when we have done this, so we know our influence coefficient matrix A, we can calculate the unbalance, and that's important for the next step, so for the unbalance compensation. And for this sake, we use in this example of the rotor 3 different balancing planes that are shown in this picture here, displayed in blue. And again, let's imagine we have a residual unbalance in a balancing plane, and to compensate this unbalance, we need to apply balancing weights on the opposite side. So we have a positive mass compensation, and usually we have to, or we divide our balancing weights into 2 weight components, as you can see in this picture here. Okay, so basically we need more than 1 balancing run. So we need to repeat this procedure at a higher rotation speed. And that's because, as I mentioned earlier, it's not possible to speed up an unbalanced rotor to the final speed. And in addition, we get a vibration reduced run up with this so-called forward balancing. So we repeat the steps 2, 3, and 4 at higher rotation speed, and we compensate the unbalance step by step. And if the tolerances for the residual unbalance are maintained, the rotor is ready and is disassembled and can be mounted into the pump. On this next slide, I want to introduce the laser balancing, and I want to explain. But Viola already has mentioned the reasons for this, why we have dared to take the step of developing our laser balancing technology further. And that's basically because of the increasing turbopump requirements, but I want to repeat some important points here. So besides the primary requirements, we have these strongly increasing secondary characteristics. And especially the vibroacoustic emissions are getting much more important. So we invented and developed the new method of laser balancing. And in this picture, you can see our laser balancing tool. And together with this tool and this technology, that enables us a more efficient balancing of our turbopump rotors. So it's an optimization because we eliminate balancing holes and balancing weights. We use a laser process, and we can fully automate that balancing process. So on this next slide, I will focus on the differences between the conventional balancing technology and the laser balancing technology more in detail. So the general procedure is similar. So we mount a rotor, but this time in the special laser balancing machine. We measure the radial displacement, we calculate the unbalance, and what I want to mention here is that the laser is capsulated in a special chamber in our laser balancing tool, so there is no danger from laser radiation. And what we can see in this figure here with the next animation is again our 3 balancing planes for this rotor, and we can see the indicated laser beam path to each laser balancing plane. And now the biggest difference for that laser balancing process is that we reverse the mass compensation. We now have a negative mass compensation. So we use the process of laser ablation, and you can see an example image on the bottom left side in this slide here. We use a high energy pulsed laser, and we heat up the rotor material locally, and that causes vaporization or sublimation of the rotor material. And so we can remove mass and rotor material at any point in form of a defined geometry. And we call this the geometry laser ablation segments. And you can see 2 of these segments at the bottom right picture. And as a result, as I mentioned, the mass is removed, but this time in the same angular position like the unbalance vector. And so we can reduce the unbalance, and we can do our mass compensation. And this process or this procedure is again an iterative process. It's the forward balancing process. And if the tolerances are met, the rotor is again ready and can be disassembled from the laser balancing tool. Okay, so now let's focus on the advantages of that developed laser balancing technology. And first of all, let's focus on the advantages for the balancing method itself. So first of all, this process is much more precise compared to screwing in step balance weights or removing mass by drilling or milling. And as a result of this, we can achieve a lower residual unbalance. The laser ablation, even though we heat up the rotor material, but we do not influence the material properties. And what's also a big advantage is, as I mentioned, we use only one single laser, but in combination with a mirror system. So it's possible to reach all these different balancing planes because we can move the mirror relatively to the laser beam. And therefore we can reach all these different balancing planes. And that gives us a greater flexibility for future rotor designs because we can define and align the balancing planes much more flexible. And last but not least, a final but still very clear advantage is that we don't use fixed balancing drill holes. So we can position the first balancing segment at the exact position of the unbalance or like the unbalance vector. And so we can reduce the mass distribution at the exact location. And in further balancing steps at higher speeds, the balancing algorithm takes into account the ablation segments that are already processed. And maybe for a better understanding, I want to show you a comparison. So imagine we have this rotor with this laser ablated rotor, and we have an initial rotor unbalance again displayed with a black arrow here. So first of all, we reduce this unbalance with a single laser ablation step at the exact location. Then at the next rotor speed, we again measure a residual unbalance, and that can be corrected by reusing the first laser ablation segment and adding another one. So with the conventional balancing, we usually have to use 2 balancing weights for the initial unbalance that you can see at the bottom left picture here. And now again, at the higher rotation speed, we have a residual unbalance that remains. And when we want to reduce this second residual unbalance, we have to reuse or we have to dismount one of the already applied balancing weights with another weight, and we have to apply a third balancing weight. So to sum this up, laser balancing usually requires fewer correction steps and is much more efficient. So now on this on this second last slide, I will focus again on the advantages, but this time for the applications. So we have a more efficient correction of the resulting unbalance, and this can be achieved because we have an expertise in our calculation algorithms, and we further developed our expertise in this topic. And we basically use the laser balancing tool with its advantages. So as we can see from this equation here, we reduce the residual unbalance. And because of this, we also reduce the balancing quality class G. And what that means is that when we have a low balancing quality class G, that means we have a well-balanced rotor with a high quality grade. And based on the reduction of the unbalanced tolerances, we can reduce either the quality class G or respectively the residual unbalance by approximately 50%. So what are the advantages now for the laser balancing for the applications? So I have talked a lot about this. We have lower radial forces, and because of this, the rotor material and especially the bearings are less stressed. This also leads to a longer service life as well as lower vibrations. And the fact that we have lower vibration that are transmitted, so we have less vibration that is transmitted over the bearing. And this has a positive effect on sensitive components and processes that are mechanically coupled to the pump. And that also results in lower sound emissions. So we have low vibroacoustic emissions. And the particles from the laser ablation are extracted and filtered during that process. And we have a subsequent cleaning step right after the laser balancing. And therefore, we can guarantee the highest level of cleanliness of the laser balanced rotors. Yeah, again, to sum this up, the use of laser balanced rotors is an optimal addition for numerous applications and devices in which low vibroacoustic emissions are required. So as Viola already explained more in detail, for example, mass spectrometers as well as electron microscopes benefit a lot from these advantages, and turbopumps with these laser balanced rotors can help to improve the efficiency of these devices. So that's almost the end of our presentation, and maybe the final conclusion to keep in mind is by employing laser balancing, Pfeiffer Vacuum was able to improve the balancing quality of turbopump rotors by more than 20%. So thanks a lot for your attention, and if you have any questions, you can of course ask them in the following Q&A session.
Yeah, thank you very much to Viola and Pascal for this really, really useful presentation with all these tips and tricks. And to all who had issues during the beginning of the presentation with sound, we really apologize for that. And you can watch the presentation again. It will be available on demand right after this session. But now we will continue with our Q&A session, and there are already a couple of questions that came in. So one viewer thanks you a lot for this great presentation, and they would like to know if there is any guide or if there are any other resources that help getting further information on balancing.
Now my sound is gone.
Yeah, I couldn't hear the end of the question as well, so it just.
I think the question was if we have some more information and guides on balancing. We do have something like an application report on our website where we discuss what are the balancing methods, what are the differences of laser balancing, and what are the advantages. So it's some content of this presentation, but a little bit more detail. And I think it's also attached to the webinar link.
Yes, so actually when users scroll down on the screen where this very webinar is streamed, there are the attachments where they can find an article and further information, further resources exactly on this topic. Yeah, thank you, Pascal. That's great. Okay, so again, Pascal, to you. So in the conclusion on the last slide, you mentioned an improvement in balancing quality of around 20% due to laser balancing. But then on the slide before that, you showed a diagram that showed a reduction of 50%. What's the difference there?
I'm sorry, I was muted. The difference is that The 50% is more a theoretical value. So as I have explained, we reduced the unbalanced tolerances in the production. And by doing this, we, using the equation I have shown, we have a reduction of 50% of the residual unbalance and the balancing quality class G. But we state that we have a real optimization of our rotor and of the complete pump. So when we take a look at the vibroacoustic emission, for example, we state that we have an optimization of more than 20%, because when we do some evaluation of the real production data, the rotors are often a little better than their tolerances. So we can state that we have an optimization of more than 20% and ideally up to 50%. But that depends on tolerances in the machining processes, in the balancing process. So that's the main difference.
Okay, yeah, thanks for explaining this further, Pascal. So Viola, there's a question that came in for you. On slide 19, you explained that other vibration or resonance frequencies also have an influence on the experimental results. Can you please explain a bit more in detail what these vibrations are and where they can come from?
Yeah, sure. So today we focused on the vibrations of a turbopump, and we showed the results of electron microscopy where with different vibration amplitudes and the high vacuum flange. But for sure, all other components of your machine or your apparatus, they are also a source of vibration. And the vibration of a turbopump is mainly at a specific frequency, for example, 1000 hertz or 850 hertz. But there can also be resonance frequencies of the whole experimental chamber, which can influence your experiment. And sometimes the lower frequencies, so below 500 hertz, they are sometimes more important for your experiment. And then the vibrations of the turbopump is not that important or not in disturbing your experiment. So for electron microscopy, it's important, but not for all applications.
Okay, thank you, Viola. There's also a follow-up question on this. I don't know, do you have any tips or can you advise on an easy way to find out if vibrations come from my pump or other instruments?
I think this is not that easy to answer. So it really depends on your application. So the best way, I think, would be to contact, for example, Pfeiffer Vacuum. You can contact your responsible sales engineer and then discuss the whole application. So Pascal, maybe you have another idea, but I think it always depends on the application.
Yeah, that's right. That can be that's a big topic, vibration analysis, and we do have some tools from the Pfeiffer Vacuum side to analyze with mechanical and structure analysis, and we also do have a acoustic camera where we can analyze where is sound emitting from. So, but I think the best way is to contact us, and then we can help more in detail, because it's a big topic and a lot of things can influence and emit vibration and sound.
Okay, great. So yeah, there's one last question that we can take during this live Q&A round. So in the presentation, you often mentioned vibroacoustic emissions on some of the slides. Could you please explain this term again?
Yes, I can do this. So maybe again, if we think of a rotor with an unbalance, this rotor has, as I mentioned, a radial displacement that generates oscillating movements and therefore radial forces. And these forces are transmitted over the bearing, and we have vibrations of the whole pump. And because now we have these oscillations of the surface of the pump housing, the molecules in the air start to oscillate, and that results in a sound emission of the turbopump. So there's always the correlation between vibration and noise emission. And so we speak of a vibroacoustic emission. But in general, if we reduce the vibration of the surface of the pump housing, we can also reduce the sound emission. So we use, as I said, because of this correlation, the term of vibroacoustic emissions.
Great. Thank you so much for explaining this as well. Yeah, and with this, I'm afraid we have to close the first session of our virtual conference. Thank you again so much, Viola and Pascal, for your great presentation. It was very, very useful, and I'm sure all our viewers learned a lot about the importance of balancing turbopumps. And everyone who joined, thank you so much. Enjoy the rest of our virtual conference and see you again very soon. Bye.
Thanks. Bye.
Thank you. Bye.